Welcome to UVU CS3060 Lecture 7.4, where I give some examples of synchronization in various language libraries. We'll talk about transactional memory, OpenMP, and functional programming languages. So in transactional memory, what we do is we set up memory accesses via transactions. The languages that support these will actually establish a transaction for change, and transactions are performed atomically. Therefore, if you perform an update, that update cannot be interrupted by any other processes or updates. And so those particular transactions are locked. And this is true for reader-writer problems. This is true for any of the transaction situations that these languages provide. There is a library called the OpenMP, multiprocess. OpenMP is a set of compiler directives. These directives exist for C as well as for Fortran. And this API supports parallel programming directly in the language. What you do is, if you want to specify a particular section that's critical, you use the pound pragma. Pound pragma is just simply a C directive that says, here's an extension to the C language. The extension you're using is OMP, or OpenMP, and OpenMP has various commands. In this case, we're using the critical command, and what that does is it specifies this block. So these curly braces define the block that is considered a critical section. And inside this critical section, the count is protected so that only one process at a time is modifying count. Now, OpenMP contains a lot more than just simply specifying a critical section. You can also create a program that splits loops apart and parallelizes those loops. OpenMP has a lot of power when it comes to using synchronization. Now, there are languages that do not operate the way traditional languages like C and C++ and C# work, or Python. These are called functional programming languages. In functional programming languages, they think a little bit different. In a functional programming language, you don't necessarily store data in variables. In C, I can assign a count variable, and I can increment it, I can decrement it. In a functional programming language, that's not something that's supposed to happen. Variables are treated as immutable, meaning that when you assign a value to a named label, it does not change. The state of that does not change. Once it's going to be set like that, it's always going to be set like that. When you say x equals 2 plus 2, x is always going to be 4. There's not going to be any difference, but you can only use x to be read from that point on. There are lots of different languages. Erlang and Scala are two that are listed here. The others that are out there, there's one called Haskell. There's a language called Lisp that's built into the Emacs editor. Scheme is another one. There's lots of languages. You'll hear frequently the term lambda calculus, which is a very common component of functional programming languages. But the upshot of having variables that are immutable is that you don't have synchronization problems. How do you overwrite data that cannot be overwritten? Thus, functional programming languages skirt around the problem of synchronization and race conditions. This brings us to the end of Lecture 7.4, where I discuss library and language synchronization examples.